In third case, what I am doing is, again I am using same tuning fork throughout the experiment, same tuning fork throughout the experiment, same weight throughout the experiment, N and T is fixed. I am going to study the relation between linear density and length. How to change the linear density? Use a wire made of different materials, copper, iron, brass, different materials, so that linear density will change. That can be total mass by total length, we can calculate linear density. Now, I am keeping N and T constant, then if I change M, L will change. This L we call as resonating length. So, take the first wire of linear density M1, take the first wire of linear density M1, repeat the experiment, that is vibrate the tuning fork and keep it on sonometer box, then vary the position of B2 until the rider falls. So, that is resonance. Note down the corresponding length L1. L1 is resonating length corresponding to the linear density of the first wire. Let us say copper wire. Change the copper wire by iron wire, that means linear density will change. Linear density will change. Repeat the experiment, note down the resonating length L2. Again replace the copper wire with the brass wire M3, L3. So, these are the resonating lengths corresponding to different wires. Now, from this, since same frequency I am using throughout my experiment, same tension throughout the experiment, then I can prove that L1 into root M1, L1 into root M1 is equal to L2 into root M2 is equal to L3 into root M3. Okay. So, that means we have finally proved that root L into root M is constant. That is the third law proved. Okay. So, now the transverse vibration of string can be experimentally proved by sonometer. Okay. Fine, this is what the idea of sonometer. Now, is there any practical applications of sonometer? Okay, no doubt we can verify the laws. Now, by using the sonometer, I can estimate the density or specific gravity of this object, or specific gravity of water, or specific gravity of given liquid. How it is possible? Let us say that when this weight is in air, note down the resonating length. When the suspended weight is in air, note down the resonating length 1 by 2 L1 by M, where N is the frequency of the tuning fork, L1 is the resonating length, mg is the weight of this. Next, keep this weight in water, completely immersed. Completely immersed. When this suspended weight is in water, mg acts down, the upthrust acts up. Due to that, tension changes, the tension in the wire changes, then resonating length changes. So, by keeping the suspended weight in water, repeat the same experiment, note down the resonating length, because since I am using the same tuning fork, 1 by 2 L2, 1 by 2 L2, root of, we know that when object is in water, weight is acting down, upthrust is acting up, where upthrust is VL DLG. If I simplify that, mg into 1 minus 1 by rho, the weight divided by linear density. I am not changing the linear density of this wire, same wire I am using. Okay. This mg into 1 minus 1. What is this rho? Where rho is density of solid by density of water, if it is water. If it is some other liquid, write some other liquid. So, we can call this, if it is water, we call this as relative density or specific gravity. Relative density or specific gravity. In CGS system, density of water is almost 1, specific gravity is same as the density of the solid which is suspended from this. Now, take the ratio of this, mg by m gets cancelled, n 1. By knowing the L1 and L2, L1 is resonating length when object is in air, the suspended object is in air, it may be sphere form or any other form. When it is in water, L2 is the resonating length. By knowing L1 and L2, I can calculate the relative density of water, relative density of the object. Okay. Or some other liquid, you keep it here, we can find out that also. So, that means using this simple sonometer setup, I can measure density of a solid or liquid. Usually in competitive examinations, they may they concentrate on the applications of this instead of derivation of this formula and all. Usually in board examinations, they concentrate on derivation of the formula. In competitive examination, the applications are more important. Okay. How this transverse vibration of string is used to measure density of solid and liquid. So, now we discussed the transverse vibrations where it appears two waves travelling along the string in opposite direction. They are transverse stationary waves formed in the string. The same type of phenomena can be observed even in longitudinal case also. In a longitudinal case, that is, take a closed pipe which is enclosed with air. The air. Okay. The length of the pipe is the same as the length of the air column. We say it is the air column. Okay. Some amount of air column we can take in a closed pipe. Now, in earlier case, I am using string. Okay. Now, I can vibrate this air column. I can vibrate this air column by applying some periodic force. I can vibrate the air column by applying some periodic force. Let us say, take a tuning fork. Take a tuning fork of frequency n. Take a tuning fork of frequency n, vibrate, and we can send the disturbance along the string. So, the disturbance travels along the air column and it is reflected from the closing end and returns back. It travels forward. After reflecting from the closing end, it travels. Okay. Like this, the disturbance travels forward, again comes backward. Like this, the vibrations are set up in the air column. The vibrations are set up in the air column. When this air column is vibrating, it produces a sound. So, These usually we called as longitudinal stationary waves are formed in air column. Okay. Just like earlier, transverse stationary waves formed in a string. Now, in a closing end node is formed. Closing end node is formed. Since the freedom of vibration is more at the opening end, an antinode is formed. Antinode is at opening end, node is formed at closing end. So, let us calculate with what frequency the air column vibrates. So, we know that the distance between node and successive antinode is lambda by 4, which is equal to length of the air column. The distance between node and successive antinode is lambda by 4, which is nothing but length of the air column, which is same as the length of the pipe. Then lambda is equal to 4L. Lambda is equal to 4L, the wavelength of the wave that is traveling along the string. And we know that V is equal to n lambda, the V is equal to n lambda, n is equal to V by lambda. What is lambda? 4L. This is the frequency of the vibrating air column, the frequency of the vibrating air column in first mode. We can call it as fundamental mode. Let us call this as N1. Let us call this as N. Here what is V? Where V is velocity of longitudinal wave traveling along the string. Okay. If it is air column, in the earlier classes we have calculated this V, where V is equal root of bulk modulus by density, okay, which is also equal root of, okay, gamma p by density. Fine. Now, by changing the periodic force, I can change the mode of vibration like this. I can change the mode of vibration like this, okay, where antinode, node, antinode and node will form like this. This is a pipe. Okay. The wave travels like this and goes like this. Okay. Then, now 3 lambda by 4 is equal to L. Okay. Lambda by 4, lambda by 4, lambda by 4 equal. That means the wavelength of the wave is, lambda is equal to 4L by 3. Okay. So, in this mode of vibration, wavelength is 4L by 3, and if I calculate the corresponding frequency, which is equal to 3 into V by 4L. Okay. And if you observe that V by 4L is fundamental frequency, in the next mode of vibration, the frequency is 3 times V by 4L. That is odd multiple of V by 4L. This is called third harmonic or first overtone. Third harmonic or first overtone. That is, second harmonic is not excited. It is not possible to excite second harmonic. Similarly, if I calculate, I will get next is N5, which is equal to 5 into V by 4L. In case of a closed pipe, I can excite only odd harmonics 1, 3, 5, 7 like this. Okay. All harmonics are not possible to excite. Okay. So, sim dash dash dash. Okay. So, up to now we are discussed what are the frequencies that can be excited in closed pipe. Okay. What is the fundamental frequency and what are the harmonics that are possible. In the next class, we are going to discuss the vibrations of air column when both sides are open. Okay. This is also open, this is also open, and what type of harmonics we can excite in open pipe.